So we have shown that the Schrödinger equation for free electron model has solutions with periodic boundary conditions if vector k has the following components. Kx is equal to 2 pi divided by L times some integer number nx, and similar structure for two other components, but with different integer number, ny and nz. So let's try to present these solutions graphically. For that, I will draw my space. So this is my kx and ky axis. Also should be kz axis, but I will just skip it. So every solution of Schrödinger equation can be represented as the point in this three-dimensional K space. So each solution that I have drawn, I will call a state. So each point is called state. And the distance in K space between two states in all directions is the same, and this is 2 pi divided by L. So because this space is three-dimensional, I have exactly one state per cube of the volume 2 pi divided by L cube. So inside of such volume in K space, I have one state. Now let's calculate how many states are there in a sphere of a radius k, which is much larger than this distance between two states. So in order to do that, I can get an approximate number of these states in a sphere if I take the volume of the sphere, which is 4/3 of pi times radius of a sphere cube, which is k cube. So this is the volume of the sphere, and I have to divide it by the volume of occupied by one state. So divide by this number means multiply by inverse number. So I have to multiply it by L divided by 2 pi cube. And I have to add something else, which is additional factor 2 in front, and this is due to spin. Because every state can be occupied by electrons spin up and spin down. So this is for spin. Okay, I can simplify my expression slightly. So 2 times 4, which is 8, can be cancelled out with this 2 to the power 3 in the denominator, as well as one of the pi's will cancel with one of the pi's in the denominator. So my simplified expression for number of states in a sphere of radius k is L cube divided by 3 pi squared times k cube. Right, so now we have to recall that in the free electron model, energy is related to a k vector, simply as energy is h bar squared, k squared, this is just a momentum squared, divided by twice of the mass, as for classical particle. So this allows us to express k vector through the energy, which is 2m energy divided by h bar. So substitution of k into the previous expression will give us n, which will be a number of states with the energy smaller than E, because now my n is function of E, not k vector anymore. So n as a function of energy is L cube divided by 3 pi squared, and here I have 2 m e to the power 3 half, and this additional h to the power 3 in denominator, I will just write it in front. Okay. So let's call this number m as the number of states with energy which is smaller or equal than energy E. And this will also allow me to introduce a new very important parameter, which is called density of states. So in some textbooks, it's also called the energy density of states, because there are few different density of states. But in this course, we will only use one density of states, and this is the energy density of states. So by definition, the density of states is simply a derivative of m over the energy. So let's calculate the density of states for our three-dimensional free electron model. So for that, we have to use expression for n, which we have just derived. So density of states as a function of energy is L cube. Instead of L cube, which is simply the volume of the crystal, I will write V. So V is the volume of my crystal, divided by 3 pi squared 1 over h bar cube. Here I have 2m to the power 3 half, and the derivative of energy will give me 3 half energy to the power 1 half. So this can be slightly, really very slightly simplified. So the density of states is volume divided by 2 pi squared, because this 3 will cancel with 3 at the end. So this will be 2 pi squared h bar cube 2m to the power 3 half and root square of energy. So please remember that this is three-dimensional case of our free electron model. So for the case of 2 dimensions, the expression will be different, and this is the part of your homework to show how different it is. So since density of states is just a derivative of m, we can also revert it and express n through the density of states. So the number of states with the energy which is smaller than E will be simply the integral from 0 to E of density of states over dE. Okay, so this is also a useful relation that we may use later.